Morning, everyone. So we're going to continue our final review in Chapter 2, which is on atomic structure. The word atom actually comes from the Greek word atomos, which means something is small. We started off this chapter here looking a little bit through history, sort of crediting some of the major scientists as with their conception of the atom. Remember, one big idea in this section here is the atom has always been the way it has been. It's just that as our technology and our data has improved, as we get more information and experimental evidence, our understanding and our interpretation of the atom changes. So it's not necessarily that the atom itself actually transforms, but the better that we kind of gather data on the atom, our understanding has to make sure it fits to match the criteria, make sure that our models are actually predicting what we see in the lab. So we start off this history walkthrough here with a fellow called John Dalton. He was sometimes known as the founder of modern chemistry. John Dalton, he was working in the 1800s. You don't need to know the year, but you do need to match up here for Dalton. He believed atoms were solid spheres. So if you took an object, let's say it's a solid, we know particles are really tightly packed together, they're vibrating in place. He had this notion here, if you were able to chop this up into small pieces, you'll eventually get to what's called an atom, which has every property that the bulk sample has, but this is as tiny as you can get them. He used words like, this atom here is indestructible, right? That's as small as you can get it. It's indivisible. You can't make it any tinier. There's no protons or neutrons. That's the tiniest. Around this time here, he believed that there were about 50 pure substances or so. He believed every element had its own atom. So copper had its atom, silver had its atom, but they were all solid spheres. Something was fundamentally different about these atoms. It took about 100 years later, we had a fellow called J.J. Thomson. He came along, he was working with really old CRT television sets, and he had actually discovered not only are atoms, right now atoms themselves are neutral, but he discovered things actually tinier than atoms that are definitely charged that were making the images that you were seeing on the screen. So he developed what's called the plum pudding model. You could also refer to this as the raisin bun model if it's easier. Basically, we believe that these, nowadays we call them electrons, with a negative charge. There are negative charges that are dispersed. Imagine baking a raisin bun. Those raisins end up just spread out randomly through the bun itself. To make sure that this new model here is actually consistent with any older model, remember for Dalton, when he uses the word here atom, he implies that the atom here is neutral. For Thomson to make sure it's consistent, even though it is good to have negative charges that are smaller than the atom itself, atoms aren't actually indivisible. He actually, to keep it consistent, he said, it's not that you can't have negative charges, it's just that you have to have the same number of negative charges as what we now know as protons. Same negative, same positives will also mean neutral. So that's the raisin bun model, negatively charged electrons in this positive background. About 5 years later, we have a fellow called Ernest Rutherford. He wanted to test whether Thomson's model, this random distribution of plums, is actually correct, and he actually took a piece of gold foil. This is not his model, but this is his most well-known experiment called the gold foil experiment. Gold was used because it was really easy to thin down to a very thin layer. It doesn't matter if it really was a single layer thick or whether it was multi-layer. Essentially, what he tried to do is he tried to send in what are called alpha particles. At the moment, we're just going to track alpha particles here has a positive charge. He wanted to see the interaction between these positive charges and the Thomson model. Because in the Thomson model, because the negatives would be just randomly interspersed, as I have positively charged alpha particles going through, because positive likes negative, it's going to experience small tugs and pulls as it tries to cut through the atom itself. That's why he had predicted if I send in a stream of alpha particles, even though alpha particles here are the weakest radiation, it should be able to cut pretty much straight through. It may experience the odd deflection, but I should be able to detect the final hit somewhere on the opposite side of the detector. Even though that was his hypothesis, being a good scientist, he actually put his detector to wrap all the way around just in case his model was incorrect, and this is actually what's surprising to him. Most of the alpha particles did go straight through, so it sort of matches with his expectation. But what's surprising here is some of those alpha particles seemingly hit a piece of gold foil and actually deflected back the way it came. He later wrote on an article, it's sort of like firing tank shells at a really, really thin piece of paper, and somehow instead of the tank shells ripping through the paper, it hits the paper and then rebounds back the way it came. This eventually developed what's referred to as the nuclear model. Instead of the Thomson model, which has all the positive background, just being that batter material in the raisin bun, he imagined that all this positive was actually squeezed into a much more dense core. So while the atom itself is still tiny, he believed all the positives, were nowadays called protons, they're in a very, very tiny center of the atom, which we refer to as the nucleus. Around the same time, we had a fellow called Chadwick who discovered neutrons. It was really hard to discover because neutrons, as the name suggests, they're neutral, so they don't interact with electric fields, magnetic fields. He had to be really creative in finding these neutral particles. But in fact, here for Ernest Rutherford's model, most of the atom is actually empty space. It's a vacuum. There's actually nothingness inside. How this actually predicted what the gold foil experiment recorded was alpha particles that happen to be on a collision course with a proton. If I'm a positive and I'm on a collision course with something else that's positive, I'm going to eventually slow down, and there really is no other way to turn except back the way it came. Most of the alpha particles, however, that are not on a collision course, they might experience the odd deflection. They may be able to get straight through. So this is starting into a more modern conception of the atom. Most of the atom is actually empty space. Electrons actually mark off how big the atom is, but in fact, most of the mass is actually squeezed into the really, really dense core in the middle. A fellow named Bohr came along, and he, using those absorption and emission experiments that we did later on in this chapter, he had figured out not only are electrons in these orbits, for some reason the orbits have a maximum number of electrons that they can handle. Electrons, although they're negative, they want to be close to the core. If the first shell happens to be full, the next electrons will have to be on the next shell, the next electrons will have to be on the next shell. We talked about later on in this chapter, actually every element has an infinite number of shells available, but you see that there's only a finite amount of positive attraction in this core here. It's not like the shells can actually go infinitely far out. So eventually what we end up seeing was the energy levels for these shells, they end up converging, because if you pull it too far out, the proton really has a hard time holding onto the electron, and in that case there, the electron completely gets ionized. It becomes a charged element. So, fleshing out the Bohr model here, we have subatomic particles, things that are smaller than the atom. So we have our PNE, protons, neutrons, and electrons. Make sure you know the whereabouts of them. Because protons and neutrons are in the nucleus, we can refer to them as nucleons, particles of the nucleus. The others are in the orbits, or they're in shells. Later on, we came back and we talked about orbitals and SPDF and all that. In terms of masses, this is actually when we define carbon. You know how we define a C12 is defined to be just 12 atomic mass units. In fact, that 12 is special because carbon actually happens to have 6 protons and 6 neutrons. Because a proton and a neutron roughly have an atomic mass of 1, if I add up the 6 protons and 6 neutrons, that's what actually gives me the 12. It's not an exact one. We're going to actually find a neutron that's actually slightly heavier. If you look in the numbers, I think it's 1.008, whereas protons are 1.007. But give or take on this chapter here, we just say 1. Relative to mass here, electrons are about 2,000 times less massive. They don't have as much substance to them. However, in terms of charge, they do counterbalance the charge directly. So a proton has a full positive 1, whereas an electron has a full negative 1. These things here are relative. They make the numbers easier to work with. If you were in physics and you were trying to actually punch things into Coulomb's equation, things like that, you would actually need to convert it back to our SI units, 1 AMU. Again, we would typically call it U, or even just say no units is the best. 1 U is actually equivalent to some 10 to the negative 27 kilograms, whereas this charge here, I always say protons are plus 1. In the actual SI unit of coulombs, it's actually referring to this elementary charge, this basic charge. Protons have a positive of this charge, electrons have a negative of this charge. So here's the first sort of style of question. We've been doing this since Science 9, Science 10. For every element, it's actually the atomic number, the number of protons that makes you the element. So let's do chlorine again as an example here. Chlorine is element number 17. Make sure we're using our IB data booklets that actually have 2 decimal places. We have these 2 numbers here. The element number I'm referring to as atomic number, which is Z. This number here actually tells you for us to be chlorine, chlorine has to have 17 protons. On the periodic table, the other number, in chapter 1, we've been using this number here as atomic mass, the mass of an atom, the mass of just one single particle. It's not really that we're chopping a chlorine into 0.45s of protons and neutrons. We'll come back to this in the next section here. What we usually do is we round this 35.45. We round it, oh, that's close enough to 35. That's the nearest whole number. When it is a whole number, we now call it the mass number. And by doing that rounding, because protons are about 1 and neutrons are about 1, I have 17 of which are protons. What I can do is I can take this mass number, let's say for chlorine, my mass number is 35, I minus off 17, which I know to be protons, that automatically gives you that we have 18 neutrons. For the really early elements at the top of the periodic table, we're going to find neutrons and protons come hand in hand, but when one extra proton, one extra neutron. About halfway down the table, we're going to see each time I move across the periodic table, I'm just picking up one extra proton, but there's so much added repulsion between those positive attractions that I need way more neutrons to actually help stabilize the isotope itself. Alright, so that's how you find protons. Neutrons come from the mass number. We always assume words like atoms and words like molecules are neutral, which means the protons exactly matches electrons. Chlorine has 17 protons, right away 17 negatives. If this chlorine has had a chance to actually bond and actually transfer electrons, share electrons, gain electrons, it may have become charged. Chlorine naturally does want to become the Cl- ion, although in this chapter we can artificially I come in with a pair of tweezers and I can pull off electrons however I like. I can make Cl+, I can make any sensitive charges, and all you need to track here, if I remove electrons, the thing has been oxidized, that means the thing is a cation. Overall we're positive, that means we have more positives than negatives, more protons than negatives. Whereas if I add electrons, more guests arrive at your hotel, overall we're called an anion, we have a negative charge because our electron number is actually bigger than the proton. The way I keep it clear here is I say, because the proton tells me what element you are, this proton number typically doesn't change. What will change here is either I lose electrons, I throw away things that are negative because then I have extra positives, I'm a cation, or I gain negatives here because I gain negatives, so I wrote that backwards, more electrons than protons, I'm going to eventually be negative overall. We can summarize this on what's called standard atomic notation. Let's say I wrote down here chlorine 37 with a -1 charge. You're going to find sometimes when they do the standard atomic notation, this isotope is actually not the one that's matched out on your periodic table. Remember, on a periodic table, this is a weighted average of the many different versions. When you're specified one particular isotope, treat this 37 here as actually the mass number. This is the other way chlorine actually appears. If chlorine actually weighed 37, 17 of which are protons, we can do a quick subtraction there. That would mean this chlorine, this version of chlorine actually has 20 neutrons. In this case here, 17 positives was supposed to mean 17 negatives, but for me to have an overall charge of -1, I have to have 18 negatives. They started out equal, but I now have one extra negative. In chapter 2, they really like asking this question here, define an isotope. The prefix here, iso, means something is the same. The part that's the same is we're talking about exactly the same element. Same elements here have to be exactly the same number of protons. That number can't change. What's different about isotopes in comparison here are different isotopes have different mass. There's different versions of chlorine. Say in chlorine's sake, chlorine can either be the 35 type or chlorine can be the 37 type. Unfortunately, on the periodic table, we're only given one spot to actually specify the mass. Do I put 35? Do I put 37? Naturally, you would imagine I want to take an average. Unlike a simple average, which takes 35 plus 37 divided by 2, which gives you 36, this simple average unfortunately assumes that, yes, we do have these two types of isotopes, but it pretends that both isotopes have the same say on the atomic mass. When in reality here in our universe, we can punch it through a device called a mass spectrometer. You do even know the name of this. We punch it through the device through a mass spectrometer, and we actually realize, although these two chlorine forms exist, it actually comes to us in a ratio of 3:1 for chlorine. So there's actually 3 chlorine 35s for any 1 chlorine 37, which means that the 35 should have a little bit more say on the average mass. What we end up doing is a weighted average formula. This formula, again, is not on any data booklet, so make sure you memorize this here. Should be fairly easy. Essentially, what the periodic table has done is here's the mass of the first isotope, but it's factored in the abundance. It's factored in how common it is, so mass percent, plus the mass of the second isotope times percent. And then if you have more than 2 isotopes here, you can just keep adding a plus mass percent, mass percent. Basically, every mass is being scaled down by the percentage. So, in this case here, if we know chlorine is the 35 type and 37 type, we don't actually need to do all the math here. So we have 35, we have 37. The simple average would put me right in the middle of 36. Because the weighted average on the periodic table is already skewed towards the 35, it's pushed towards that way. I know in this case here, there's more of the lighter isotope. They might then afterwards actually to flesh out what abundance distribution would actually give you exactly 0.45. Remember, no single chlorine actually weighs 35.45, but if you have a handful of chlorine, some of them are 35, some of them are 37, given more of them are the lighter type, it's like on average, overall, these atoms all weigh 35.45. So that's that notion here of doing weighted averages that fleshes out how come there's decimals. This was really good for us in chapter 1. We didn't really know about isotopes, and we just said, oh, if I react chlorine, and now this weighted average has already said, well, on average, even if you compensate for the fractional abundance, the mass of all the chlorines is kind of like 35.45. So I mentioned here the name of the device that we use to actually measure these abundances, to measure what isotopes we have, is called the mass spectrometer. Well, we're going to do this a little bit more in the grade 12 spectroscopy unit. But essentially what's going to happen here is different masses of isotopes will be sent through this device. We're going to start off with a magnetic field, which is supposed to be deflecting these atoms here. At first, with no magnetic field, all the isotopes just hit the far end of the detector. As I slowly ramp up the deflection, slowly ramp up the magnetic field, some of the lighter isotopes are starting to change the trajectory, and they're going to actually make it all the way down. If I happen to be too heavy, unfortunately, I'm still going to collide with the opposite side. I don't actually get counted. I ramp up the magnetic field a little bit stronger. Those light isotopes which made it before are now going to be bent way too much. They collide with the close side. The heavier isotopes which didn't quite make it at the low setting, at the higher setting, they end up making it all the way down. And essentially I have it plotted. It is an M per Z or M per Q. Q is measuring charge. If we've ionized things properly, that things are positive 1. Mass divided by 1 is basically a mass. So what we get here is called a mass spectrum. We get a spread of the different isotopes. In this case here, we basically scan through the different magnetic fields. I spend the same amount of time at each setting. With a weak field, there's no hits. As I slowly strengthen, I get some hits here, no hits in between. I basically figure out how many actually hit based on which magnetic field setting that I'm at. So that sort of explains to you here, the percent abundance is given by it's the area under the curve, or basically the height of this bar here, and which isotope is actually just going to be matched up. Because this is an M per Z, this will actually tell you what mass actually exists. Next part here we studied here was a part called nuclear chemistry. Remember, nuclear chemistry is really strange because most often in chemical reactions, we predicted that it was valence electrons that got transferred around, that was sharing electrons, things like that. In this case here, it's actually reactions of the nucleus. It's actually the nuclei, the center of the atom, that's actually going to change. We're actually going to be losing protons. Say in alpha radiation here, we shoot off an alpha particle. An alpha particle here is a helium nucleus. Imagine I have radium here. The radium has 88 protons, and through the radioactive decay of alpha decay, I actually remove a daughter particle, which also takes 2 protons. It actually has 2 units of mass, and now suddenly we're a tinier element. We're now only element number 86. Because proton numbers makes me this element, the proton number has changed. I'm now a totally different element. In this example, I was radium before, I'm now radon afterwards. You don't need to predict whether it's going to be alpha, beta, or gamma, but being told which type of radiation, you should be able to predict what's the left or right isotope. In this case here, strangely enough, if I was radium on the left side, I'm not necessarily radium on this side. Fortunately for us still, the nucleons, the number of particles has to still be conserved. So for example, I had 88 protons to begin with. Even though I shoot off 2 protons in my alpha particle, I still have to have 86, right? 88 minus 2 is still 86. So the math of it, this subscript here and this subscript, 2 plus 86 has to give 88. The alpha particle takes 4 units of mass plus the 222 of the radon isotope. That adds up to 226. Even though the element itself is unchanged, at least the math of this ends up working out. So the top numbers add, the bottom numbers add. Just careful, the top numbers, when you add them, the top number is the total mass number, including protons and neutrons. For beta decay here, what's actually happening, strangely enough, is we actually have a neutron. A neutron is actually converting itself to become a proton and an electron. That's why I said earlier, neutrons are ever so slightly heavier than a proton. I believe neutrons are about relative unit 1.008. This is about 1.007. Yeah, practically they're about 1, so the mass number doesn't change. So a beta particle is basically an electron, but this electron actually gets emitted from the core. So if you imagine here in this example, we have iodine. Iodine already had many shells. It had many electrons out here. We'll do that with the Bohr model later on. But in this case, we're going to take one of the neutrons inside iodine's core. The neutron itself becomes a positive proton, and when that electron gets emitted, you notice where that electron comes from is actually directly from the nucleus itself. Other than that, it's identical to the electrons outside. Again, we're changing something with the number of protons here, so we're going to be a different element. We used to be 53. We're going to put a -1 as a placeholder here because I'm going to end up with having the element with one more proton. 54 minus 1 will give me back the 53. So alpha, beta, we're getting to the strongest radiation. Beta is about 100 times stronger than alpha. Gamma is about 100 times stronger than beta. Gamma particle, even though we really only see this with chemotherapy and deep in space, basically what we have here is any extra energy that we don't need gets radiated off. I mentioned during our lessons here, one reason why we might be unstable with this star here, one reason why is it's possible that maybe our protons all happen to be really close together. Protons actually hate each other. They're constantly trying to repel each other. Positive pushes positive way. Part of the job of the neutrons is actually to help space out the protons. So in a situation where my protons are all really close together, maybe the neutrons can reorganize themselves a little bit here. They can kind of squeeze in between the protons, spread out the protons ever so slightly, and even with that slight increase, we're going to actually have a slightly more stable form. We release off any extra energy as gamma radiation. There's our symbol for gamma, and we go from the starred form to the more ground state, the more stable form. So whenever you're asked to write the nuclear equation, you would predict it exactly like that, alpha, beta, gamma. Putting some numbers to this here, we did this with the notion of half-life. Remember, radioactivity is a random event. Let's say I have 100 grams of sample. Because it's random, I cannot point my finger to a single atom, and I can't predict for you, this atom's going to be the next one to decay. But what's going to happen here is, given a bulk sample, given many atoms, again, I can't predict. It's totally random. This one might decay, this one might decay next, it might take another 1,000 years, then this one decay. I won't be able to predict which atom decays, but what I can wait for is how long until half of the sample here decays. So let's say I go from 100 grams down to 50 grams, so half of the particles have actually either decayed away, or their radioactivity, their activity, how dangerous in reactions they are has sort of decreased by 50%. We call that time there the half-life. Every element has a specific half-life, some on the order of split seconds, and some of them on the order of millions and millions of years. So I lost 50 grams of material in that first step here. If I wait again exactly a half-life, you might imagine that I lose the other 50, but remember, because we're dealing with a probability here, we now have half the number of particles from before. As these ones here decay at exactly the same rate as afterwards, if you wait a half-life, you're only down to 25. So what we're getting here is tracking sort of an exponential decay. After the first half-life, we're 50%. After the other half-life, we're 25. Technically speaking, this one here will never reach 0. It's asymptotic. But we're going to just essentially, if it's so tiny that we can't measure it anymore, essentially it's all gone. For radioactive materials, radioactive waste in our nuclear power plants, so far one of the solutions have been we sort of encase it into glass or solidify it in concrete. We dig it into a place that's really geologically stable, and we hopefully just let it wait out its half-life. When they put numbers to this here, you do have this equation here on your data booklet. So we have this one here is the remaining amount. Careful the wording of the problem. They may ask you how much has decayed. This one here is not how much decayed. For example, if I have a substance that's 90% decayed, that means 10% remains. And it's actually the word 10 that I'm actually going to be punching in for NT. This is how much is left over. It's an exponential decay based on your starting amount. There's my rate, and then we have a T over T half. The top T is actually the real time that I wait. I'm going to call that the elapsed time. The other one here is I'm going to think in units of half-life. This one here will depend on your element. If I wait exactly a half-life, sweet, 50%. If I wait exactly 2 half-lives, right, it's going to be 25%. We only really need this equation if I'm like, let's say 1 and a bit half-lives. Because it is an exponential decay, because I'm going to lose always more at the beginning and the rate of decrease actually drops, I actually need to use this exponential formula to actually solve my way for elapsed time, maybe an unknown half-life, some numerical examples for there. So that was really weird chemistry because that's nuclear chemistry, that's changing elements. You were one element before, you're now a totally different element afterwards. For the remaining part of this chapter here, we went back to a regular Bohr model, regular chemical reactions. We already talked about Bohr doing experiments where electrons, yes, most of the atoms are actually empty space, but electrons have some maximum. The first shell happens to only be able to hold 2 electrons. If I were the third electron, although I also want to be close to the positive core, opposites attract, electron here will end up, fine, I'm going to go to shell number 2. We plotted this out on what's called the energy level diagram. We're going to plot out sort of the potential energy for being a certain distance from the core. It's definitely the most stable for electrons to be really close to the core. Remember, low energy means more stable. Instead of just drawing single dots here, as we move towards the electron configuration, we use this upspin and the downspin to indicate which way the electrons are actually twisting. If I couldn't fit on shell number 1, I'm going to figure out what shell number 2 is, and I might be the next electron shell number 2. We always do our Bohr model here. We always off-ball, so we always sort of build up. Building up meaning electrons go closer to the core when they're able to. We can also refer to that as a ground state atom. That's the most stable position it could be. We did experiments later on that, let's say with electricity or with light sources, if it's exactly the right energy, electrons on a lower shell can actually jump up to a higher shell. That's going to absorb energy. It's going to be a very unique energy. Nobody has the time to actually fine-tune the energy so detailed. So what the electricity did in our lab, or even in chapter 3, we just send in all the colors. We send in all the energies that it can possibly need, and it's going to suck away whichever color. That's exactly the size of this gap. So remember, Bohr didn't know this notion of discrete shells here. He actually did this experiment with line spectra. He ended up seeing how come elements were actually different from other black body sources as he had from before, and he actually rationalized these elements are sort of more like a staircase than a ramp. This staircase here involves electrons. They can jump up and down the staircase however they like, but every time they jump up and down, there's always a very unique amount of energy that's being transferred. Either energy that's absorbed to jump to higher shells, or in this case here we see that electron is now bored and it falls back to a lower shell, falls back to the more stable configuration. It's going to end up releasing off a photon. A photon is a packet of light, and that packet of light will have exactly the energy spacing between the energy 2 and 3. When we draw this energy level diagram, it's definitely not to scale. The difference between 1 and 2 is actually bigger than even 2 to infinity. Right? So that just sort of puts in perspective for you. We talked about there's a limit to how far out the shells can get. There's only so many protons. So when we think about a Coulomb attraction in our next chapter, if we are too far out, the protons are really having a hard time holding on to that electron there. So that actually limits us in terms of radius. That means that when I go farther and farther out, the jumps from these really farther out ones, let's say 10 to 2, 9 to 2, 8 to 2, these ones here are going to be a lot closer together. On the high energy side, on the high frequency side of the spectrum here, we're going to see the 10 to 2, the 9 to 2, the 8 to 2. We're going to actually get it relatively spaced out. They will be looking for this convergence on the high side. Careful when you're doing problems, they don't always put high energy side on the left side. Sometimes they put it on the right side, but it converges at the high side because the shells themselves are stacking up. The transitions, let's say this one here was 10 to 2, the one right beside it, let's say it's 9 to 2. The gaps between them are actually getting closer and closer together because shell 8, 9, 10 are getting really, really close. So, some other terms here. We have the main energy level, or the shell number. We use n for that. If you like, you can memorize this equation 2n squared. Essentially, this gives you the maximum number of electrons. Let's say I'm on shell number 1. If I go 2 times 1 squared, well, the first shell can only hold 2. Energy level 2, 2 times 2 squared gives us 8. Energy level 3, 2 times 3 squared gives us 18. The Bohr model is sort of limited, that the Bohr model only shows valence electrons. When we look at orbitals, the only ones that count for valence are s and p orbitals. So if you want to do Bohr models for elements in the 4th row, 5th row, you're always just going to go 2, 8, 8, 8, 8, 8. Okay? There's no 18, there's no 32 or anything. What this 18 can actually be subdivided, well, on energy level 3, we actually have 8 electrons that can fit on the 3s and 3p, but we actually have 10 electrons that can fit inside the 3ds, and in total, 8 plus 10 makes 18. We cannot draw those inner d electrons on a typical Bohr model, which is why we needed to go to that electron configuration model. Some of the names here, we have the valence shell is the outermost shell. It's always the outermost shell that does the reactivity. So I don't care how many other electron shells I have inside, those just come along for the ride. For atoms actually to react, they actually need to collide and bump into each other. Things that are isoelectronic, we see that prefix iso again, something is the same. In this case here, they have the same electronic structure. They may look the same, they have the same placement of electrons, maybe they both have 3 full shells, but they may still be different elements because the element depends on the number of protons in between. Just because I'm isoelectronic doesn't necessarily mean I'm the same size. I can have 3 full shells and be that large. I can have 3 full shells and be this large. Remember the radius, we'll do this more so in chapter 3. Radius depends on how many positives are in the core. If I have less positives, it has a hard time holding onto those electron shells. If I have more and more and more positive in the middle, although the nucleus itself is actually larger, it's actually the increase in positive charge that actually pulls in these electron shells here tighter. So, a little bit more background in terms of the EM spectrum. You do have the EM spectrum on your data booklet. They really want to put an emphasis on these 2 equations here. We have the Planck equation. Basically, the energy of photons is proportional. The h here is Planck's constant. You have the Planck's constant in the data booklet as well. It's the 6.63 times 10 to the negative 34 number. But energy is proportional. They're using nu, or you can use f for it, proportional to the frequency. So high frequency definitely means high energy. But when we look at the universal wave equation, we had the equation here. I already manipulated for you here. But universal wave equation was c equals f lambda. These said that the frequency and wavelengths are opposites. All EM waves, so all light travels at this constant 3 times 10 to the 8. This assumes vacuum. When we go through different media, different background, this number might change. But for 2 numbers to multiply to always give this constant 3 times 10 to the 8, as the frequency increases, the wavelength has to drop. So that says that those 2 are opposites, and we have a slightly rearranged form into that equation. So make sure you know these 2 equations. Also on your formula sheet here, Planck's equation, the energy is proportional to frequency, whereas frequency and wavelengths are opposites of each other. When I have high frequency, we actually have a shorter wavelength. If I pretend to draw the purple photon here, we have the wavelength, which is actually fairly tiny, fairly tight. If I imagine I was on a metaphorical boat, as this purple wavelength zips by you, you're going to bob up and down a whole lot more times because between peak and peak is actually not that far. Compare it to, let's say, a red wavelength or even longer wavelengths into the infrared and all that, this frequency is still going to be fairly large. I'm still going to bob up and down quite a lot, but as this red photon here passes you, because this wavelength, the distance between peak and peak is much farther away, I'm going to bob up and down relatively a lot slower. Maybe on the order of 10 to the 8 as opposed to like 10 to the 12, 10 to the 14, depending on the energy. Even though I am understanding this light wave here as a wave, remember it's not like the photon itself actually zigzags back and forth. This is just a way to represent what's the energy difference. We talked about 2 main terms here. We focus mainly on emission spectra in this chapter. We're going to do absorption spectra in chapter 3 again. The 2 key words here are absorption. You have to gain energy and you always jump up in shells. In this case here, once the electrons are done and they're bored, they're going to eventually fall back downwards. They may have been excited to like shell 5 or shell 6 or whatnot, and essentially when they start falling, they're jumping up and down the staircase. If they fall with a big gap, so in this diagram here, they actually meant to say this first gap here, this is a really, really huge gap, so that gives you a purple photon. It's actually light that gets released. If I compare that to a smaller transition, the electron is just falling down shell 2, shell 1. That gap there, although it is fairly big, it's smaller than the 5 to 2 gap that I showed for purple. In this case here, it gives you red, and there we see that convergence. Convergence indicates that there's a limit to how far the radius can get out from each other. So elements showing this line spectra actually was demonstrating to Bohr. For some reason, these energy shells are actually quantized. Remember, every element here has a different number of protons, so although every element has the same ordering, it has a 1s, then a 2s, and a 2p, if you compare hydrogen's energy level diagram to helium's energy level diagram, depending on how many protons I actually have in the core, my energy shells themselves, these energy spacings, maybe another element has 1s a little bit closer, maybe the 2s is a little bit closer, everything will be quantized, everything will still be in a staircase, but the actual exact staircase, the actual sizes of these steps will actually depend on the element, which means the overall line spectra that I get will end up becoming a fingerprint for that element. This is how astronomers actually figure out when they point their telescopes into space, how do they know what the composition of a really, really far away star is, they actually figured out the light that's released from it, and basically tracking the energy, they can compare it to element signatures that they know, and actually figure out the abundance, figure out how common these transitions are to actually figure out which elements are present. They say you don't really need to know these main names anymore, but it doesn't really hurt here. For a Lyman series, because electrons can fall any which way, let's say I'm on shell number 6, there's so many ways I can jump downwards. Instead of worrying about a single electron, what I'm going to instead do is I'm going to focus on a final ending position. So if I imagine all the transitions to n equals 1, that would include 2 to 1, 3 to 1, 4 to 1, 5 to 1. All those jumps are really big. You see that those arrows are large. We're going to call them the Lyman series. Lyman does refer to it being hydrogen. So the second you see Lyman, or later on Balmer and Paschen, they all refer to hydrogen. Although for other elements, you could likewise do changes to 1, changes to 2 for Balmer. For Balmer series, this is the emission spectra. This is the visible region. Turns out when I go 3 to 2, 4 to 2, 5 to 2, we notice that these arrows are much smaller than the ones before. For us, for hydrogen, we end up realizing these arrows actually fit in the visible region. For the emission spectra of hydrogen, so we have a 400 nanometer, a rough purple side, and a 700 nanometer, a rough red side here. We're going to get 3 to 2 being on the red side. We're going to have maybe a green color line, a blue color line, and a purple color line. Yes, there actually are other transitions that also fit in Balmer. If I start going 7 to 2, 8 to 2, and all that, that all is Balmer series, but that's already pushing itself into the UV region. You'll notice that when I did this emission spectra, I had drawn the lines closer together to demonstrate that convergence. They will be looking for that. Fortunately for us, this Rydberg equation doesn't come out very often, but we just did it for completeness sake here. This actually gives us a nice link. Only for something that's hydrogen-like, things that only have one electron, we have this equation that actually tracks. If electrons jump from Ni, a starting shell, to an Nf, we can actually figure out what the wavelength of the photon that gets released. Remember, electrons are stuck on the atoms. They're just jumping up and down. What's ending up giving off is actually a light particle. We can rearrange this wavelength here into using the universal wave equation. C is equal to F lambda. Lambda here. And energy is proportional through frequency. And we eventually derived a much scarier equation. But that more so links the energy of the photon that gets released based on the jump that the electron does. Sometimes your textbook will actually have the Rydberg equation written slightly different from this, which is why they might actually have a slightly different constant. But in this way of representing it, we're going to use this constant here. Very last part here in this chapter here, we needed to modify the Bohr model. We started from a Bohr model. Let's do an example of, let's say, lithium. Lithium has 2 electrons on the first shell. As you do the Bohr model second shell, I go single, 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 single. I know that doesn't quite match up with the electron configuration model. For sodium, it's on row number 3. It's an S block, so I know it has 11 electrons. Careful of the terminology here. I can ask you for an electron arrangement. An electron arrangement is actually not configuration. Arrangement is just as simple, starting from the first shell. Well, I have 2 on the first shell, 2. I have 8 on the next shell. I have 1 on the next shell. This one here is an electron arrangement. Sometimes they use comma, sometimes they use dots. Essentially saying shell number 1 is 2, shell number 2 is 8, so on and so forth. For a configuration, what we started doing here is we started realizing, well, energy shells, these orbits here aren't all the same distance from the core. Energy shell 1, sure, it's just a 1s, but at least shell number 2 actually becomes 2 floors, a 2s and a 2p. These orbits actually split into what are called orbitals. We're just using the SPDF as placeholders for them. We still off-ball. We still build up electrons lowest to highest. We start filling in the lower shells. We only start occupying the upper shells as we start filling them up, especially when we get to what are called degenerate orbitals. Degenerate meaning these orbitals are equal energy. These are equal distance and equally good to sit in. This is when we do our Hund's rule, which basically says I'm going to prefer to take my own seat until I really have to pair. For convention's sake, we always put in the upspin first, and then we come back. If we have enough electrons, say in sodium, we pair, pair, and pair. Pauli exclusion told us here every orbital, orbitals max at 2 electrons with opposite spin. So why is it I can eventually write down something like 2p6? Doesn't that mean I have 6 electrons in an orbital? No, because every room itself is an orbital. Every room itself can hold 2. Because I happen to have 3 p rooms on every floor, I can hold a maximum of 6, and in total energy level 2, we see that it holds 8. By the time shell number 3 splits, right, 3 is going to actually split into 3s, 3p, and 3d. Remember, when shell 4 also split, shell 4s actually ends up lower energy. There is no x-axis to this energy level diagram, but 4s actually happens to be lower than 3d. They're actually fairly close. That was important for us in chapter 3. But basically, as you start filling in electrons, as I start filling in these shells here, I do fill in the s's before I start filling in the d's. These 3d electrons technically do belong to energy level 3. IB likes putting them together. Let's say I was doing a configuration here, argon, 4s2, 3d10, 4p6. IB would prefer to actually put the 3d in front. The left and right order doesn't matter as long as the order that you're filling them in actually matter. This way here, the 3d10 will be right beside the 3p6 I had from the earlier shell, and that way I can track all energy level 3s together. Again, S and P count for valence. Those are the ones that the Bohr model predicts. These D's and later on the F's are all inner electrons. They don't participate in reactions in the same way. So we just recap some of those there. SPDF, we did our off-ball. Core notation uses the noble gas to actually hide the inner shells. It's eventually the outer shell that actually matters anyways. So the noble gas, most of them end with P6. It could be helium, neon, or whatever. We can hide that as a square bracket core notation, and I can add the last shell. And very end here, we can also get charged, so I can pick up negatives, I can gain electrons. That process here is called a reduction. When an element is reduced, more electrons are at your hotel, you end up putting them in the next spots that are available. Right? You've been filling them lowest to highest anyways, negatives are fairly easy. For cations, there was a very special ordering. We always remove the p's first, s, d's, and f's on the outer shell. So back to this example here, we had this configuration. We've been filling them. I had 4s, I had some 3ds, and I had some 4p's. Even though I've been filling the 4p's here, we're going to be on the outer shell. Core notation does a really good job of this. I'm not allowed to touch any inside shells, any of the 2s2, 3s2, any of those inner shells until this outer shell gets removed. As I remove electrons, if I have p's, these are the ones that actually come off first. After which, if I remove all 6 of those ones there, even though the D's at first were higher energy, because the S's are spatially farther out from the core, I'm going to remove the S's before I touch the D's. What I'm picturing here is a orbital diagram. Your p orbitals, make sure you know the shape of it. It's a dumbbell shape. They're all 90 degrees from each other, px, py, pz. There's parts of the p orbital that are farther out than the s orbital. But the d orbitals, even though they are relatively high energy, they're all really tightly held to the core. Those ones there are the last ones to come off per floor. And that's why we had that order PSD based on the outer shell. So that's a quick summary of Chapter 2. If you have any questions, feel free to let me know. We'll come back tomorrow for Chapter 3. Thanks, guys.